Cool. Okay. So let's do a little review of what we did last time. And yes, you should be able to see it, Matthew. It should say in the top left-hand corner, it should be like recording very ominously. So as kind of a quick review, let's say recall. Yeah, why? Okay. Why is it not clicking? Why can't I change colors? Very weird. Very weird. Let's try that again. Okay, can I? Okay, we're going all in gray today because I, for whatever reason, am not capable of changing colors. Okay, you don't care though, right? You don't, the multimedia doesn't matter. So let's say recall. That the limit as x approaches c, f of x is equal to L precisely if for every epsilon greater than 0, there exists a delta, such that whenever we're within a distance of delta from C, but not equal to C, right? That's important. Then the distance of f of x to L is less than epsilon, like so, right? And we did a couple of examples of that, and I left you with one example. I think I just left you with the rational function in order to be able to do. Hopefully you managed to do it, but again, if you for whatever reason are having trouble or struggling with it, throw it on Piazza or throw it on the UTM Math Discord, and lots of people there will be happy to help. I mean, most rational functions are kind of treated the same sort of way. Probably what you should have had is you should have had your x minus c term in the numerator, and then you had some term in the denominator that you had to bound. And so, the trick was, how do you bound the denominator? And you use the typical trick of saying, suppose delta is less than or equal to 1, yada, yada, yada. And you can bound it exactly the way that you want, okay? So this covers two-sided limits. Now, today, what I want to do is actually talk about one-sided limits. And one-sided limits are probably what you would expect them to be, right? So we can say definition. So we say, suppose that f maps D to R and C is some point in R. If f is defined on some interval, this is again, like, you remember in the definition of a deleted neighborhood, or when we were doing the definition of limit, there was this nonsense about f being defined on a deleted open neighborhood of the point C. This is the same sort of thing, but now for one-sided. So if f is defined on some interval c plus rho greater than 0, then we say, so again, we just need to talk about the function actually being defined to the right of the limiting point. Then we say that the limit as x approaches c from the right, f of x is equal to L if, and then same sort of story, it's exactly the same definition. It's just now, instead of looking at the two sides of the, instead of looking at both the left and the right, as we approach C, we're just going to look at the right. Like so. Okay, and then when you want to define on the left, the only things that you need to change, and again, I can't unfortunately change color here, but the things that you want to change are this, and then you want to change this to being the other side as well, right? Or maybe I can just include that in as well. So very quickly, because I know in first year especially, you get very kind of freaked out, right? If something is not explicitly defined, so I'll tell you what it is. So similarly, the limit as x approaches c from the left, and again, our definition here is not going to work out perfectly because I said the function is defined on c plus rho. So, in your brain, change that to c minus rho c. but exactly the same definition, except now we're only going to look at the left of C like that. F of x minus L less than epsilon. Okay. And as an immediate note, the two-sided limit exists if and only if the one-sided limits, both one-sided limits exist and are equal, right? So immediately, and if you're not certain about that, the proof's not hard, but again, it's a nice little exercise just to go through and convince yourself that it's actually true, right? So immediately, the two-sided limit exists. Maybe let me just write it. So the limit as x approaches C, f of x equals L, if and only if both of these limits exist and are equal. All right, it's not just enough that they exist, because they could exist and be different things. They exist and are actually equal as well, right? So we know that immediately that is true. So let's do an example. And the reality is that when you do an example of these sorts of things, they're almost always exactly the same sort of thing that you would do for a normal epsilon delta, except you just have to be a little bit more careful about whether you're greater than C or whether you're less than C. And in fact, it can often be, in some cases, easier to do the proof because you're only looking at one side versus both sides simultaneously. So, I mean, the first example that we're going to do is going to be a very simple one. All right, so example. So let's say show that the limit as x approaches 0 from the right of x divided by the absolute value of x is equal to 1. Okay. Now, if you went into Desmos or something and you graph this, you actually see this function has a big jump discontinuity. And we haven't talked about what the word continuous means, but like basically, you know, it's -1 from the left and +1 from the right. And so you really want to take the one-sided limits. When the function approaches the limit from the left-hand side above, is the delta supposed to be a row? No. So what the row is, the purpose of the row here, and now I'm really going to wish I had multiple colors. Oh, wait, no, that didn't work. Okay, so the purpose of the row here is to say, look, the function is defined. Let's maybe draw a line here. Here's C. And all I'm saying is the function is defined on, say, this interval here. Right? And so this row is like fixed. It doesn't depend on epsilon. It just says that the function is actually defined somewhere to the right. And similarly for the limit as we approach from the left-hand side, it's the same sort of thing, but now it's going to be C and then C minus rho. Right? And we still get this distance of rho here. And then the delta, so the delta is, you know, has to change with epsilon. So if, as you give me different epsilons, you give me different deltas too. Right? And then we just guarantee that delta interval has to live inside of the rho interval. That's sort of what's going on. So the C plus rho and C minus rho C things are just a guarantee that it actually makes sense to talk about the function to the both to the left and right of C, right? That's what they do. Okay, so we want to show x divided by the absolute value of x is equal to 1. If I approach from the right, so it's an exercise. If you want to do approaching from the left, the answer will be -1. And this is the sort of thing that if you were actually trying to do this both sides simultaneously would actually be very hard, in part because the limit doesn't exist, but because you're dealing with this absolute value. Dealing with one-sided limits and absolute values is actually really easy, because if I approach 0 from the right, I know that x has to be bigger than 0, and that allows me to get rid of the absolute value, right? So that's sort of what's going on here. So solution, again, it's going to be, you know what, I think I can go straight to the proof with this one. So let's say let epsilon greater than 0 be given. And you can actually set delta to be anything, but I'm just going to set delta to be epsilon. Anything would work because the function's actually constant. It's piecewise constant, right? It's actually constant when x is less than 0 and when x is greater than 0 as well. So, but I'm just going to set it to be epsilon. Note that if x is in 0 delta, right? Because c is equal to 0, so c plus delta is just 0 delta. Then x is greater than 0, right? So the absolute value of x is just equal to x. And then we would get, and so if 0 is less than, no, I've already assumed that x is in 0 delta, is in 0 delta. And so f of x minus L is equal to x divided by the absolute value of x minus 1. But the absolute value of x is just equal to x. So this is just going to give me 1 minus 1, which is 0. And that's definitely less than epsilon. This is why I said you could use any delta, because actually the function was constant. So voila, we've got what we want. Okay, and like I said, you should, as a nice little exercise, something that should only take a couple of minutes, try showing that the limit as you approach 0 from the left is equal to -1, right? And the proof is almost identical. But, and you know, don't just parrot what I've written, make sure that you can actually do it yourself, but you'll see kind of how the restriction that we're approaching 0 from the right or from the left actually makes this a problem tenable. And I think in some cases even easier than a, you know, two-sided limit. But maybe you're saying, okay, this was kind of like a silly example. Let's do a real one. So let's do something like this. Here, I made a terrible function. So here's a function. So define f from R to R by this thing. All right, some big, ugly piecewise. Let's see, what did I do here? So I said it was 22. This number doesn't matter. This is the one that's going to matter, 3x squared plus x. And then -4x if x is less than or equal to 0. All right, show that the limit as x approaches 1 from the left of f of x is equal to 4. Okay. Now, I guess something I should point out is, you know, the real problem, if you think back to high school, and I think probably most of you have done high school calculus, and if not, you should talk to me because, well, I mean, I'm not going to ask you to do anything complicated, but the benefit of high school calculus is that it actually tells you how to find limits, right? And something that I haven't mentioned here is that, you know, one of the problems with epsilon delta proofs is you have to know what the limit is ahead of time, right? So here I'm saying, you know, show that the limit is equal to 4. But as the function gets more complicated, you might ask, well, how do I figure out if the limit is 4? How do I figure out what the limit should be so that I can actually go about improving it? So this is kind of one of the, you know, downsides of epsilon delta is you have to know what the limit is before you can even prove that the limit exists, right? And so that's kind of what they teach you in high school calculus is all these methods for actually computing what it should be. And then really what you would do is you'd go through and do the proof. So you'd compute what you think the answer should be, and then you would prove it using an epsilon delta. And for our purposes, though, I'm not going to ask you to do a bunch of crazy limit calculations. Who cares about that? So we're kind of just going straight to the proofs, but just kind of realize that this is something you have to know before you can do your epsilon delta, right? You have to know what you think the limit should be. Okay, so hopefully you can all kind of see what's happening. We've got this 3x squared plus x thing. And as we approach 1 from the left, basically the idea is that the middle function is the only function that matters, right? Because I'm approaching from the left of 1 and to the left of 1. If I don't go too far so that I'm less than 0, as long as I stay between 0 and 1, then my function is 3x squared plus x. And you say, yeah, okay, I believe that thing converges to the number 4, right? Now, as part of my argument, do you remember when we were doing quadratics and we had to do this bounding thing where we said, suppose delta is less than or equal to 1, or, you know, suppose that the absolute value of x minus c was less than 1. So what I want to do is I basically want to do that immediately because I want to say I don't want x to be less than 0. I really want to look at the interval 0 to 1, right? The open interval 0 to 1. That way f of x is exactly 3x squared plus x, right? And I don't have to worry about what happens if I go too far to the left, right? So that's sort of what I want to do here. And again, it feels a little bit weird because when we were doing quadratics, we did it because it was necessary in order to bound one of these nasty functions that showed up. And here I'm doing it just out of convenience, right? So it's a little bit of a different flavor, but it's the same sort of idea. So immediately, I'm going to demand that delta is less than or equal to 1 so that we're working on 0, 1, right? Again, and if you don't see that, remember we're working on C minus delta C. C here is equal to 1. And delta is going to be, I'm basically setting delta to be equal to 1 for the purpose of this approximation. So that gives me the interval 0 to 1, right? If it was two-sided, it would actually be 0 to 2, but because it's just one-sided, it's 0 to 1. We say that note on this interval, on 0, 1, the function isn't stupid piecewise, it's just 3x squared plus x, right? So that's very, very nice. And then we can just go about doing our normal epsilon delta proof. So, and then, I'm still doing rough work here. And I said I would only do rough work. I'm generally not going to prove things. So we get this nasty quadratic. You can factor it. I factored it ahead of time. This is not a course on factoring. If you want to go plug this into into Wolfram Alpha or something in order to figure out its factorization, go ahead. I don't care. I don't care if you know how to factor or not. That's not one of the things I want to do. Again, I have a good thing here. I've got a bad thing here, this 3x plus 4. But it's super easy to bound this absolute value of 3x plus 4 here because, again, we assumed that x is in 0, 1, right? So the biggest that the absolute value of 3x plus 4 is, you might have to think about it for a bit and convince yourself, but the biggest it could be is 7. Like that. So this says, 7 times, there we go. So take delta to be the min of epsilon over 7 and 1. Right? So, okay, we were going to have to do the bounding argument eventually anyway, just because this 3x plus 4 showed up. But I did it early, just so that I could guarantee that I was always kind of in the region that I wanted to be. Why is this 3x plus 4 bad? This goes back to this idea that, again, I control what x minus 1 does, right? I'm trying to make f of x minus L less than epsilon, right? I eventually want this thing to be less than epsilon. And because we get to choose what delta is, I can make the absolute value of x minus 1, in this case, as small as I want it to be, right? So I have complete and total control over what the absolute value of x minus 1 is. That's why it's good. I have no control whatsoever over the absolute value of 3x plus 4. That's why it's bad. And so we want to bound it so that I can get rid of that and just replace it with a constant. Why can it equal 3x? Well, it doesn't matter. If you're less than or equal to as well. You might say, oh, I'm never actually equal to 0, which is, I imagine, or never actually equal to 1, which is your argument. And so this thing will never be equal to 7, but who cares? It doesn't matter, right? There's a strict less than sign that will eventually show up. And we know that the epsilon delta definition actually doesn't care if you use less than or equal to, right? But 3 is less than or equal to 7, for example. This is a fun thing that I always, it's a funny thing. If you look at the 137 piazzas at St. George and UTM, people will always say how can 3 be less than or equal to 7, right? Because it's not equal to 7. And you're like, yeah, but that's what the or is for, right? It's either less than or it's equal to. In this case, the equal part won't be true, but who cares? It's still a true statement, right? Yeah. Can we use 3x minus 1 squared? Let's see. That's an interesting factorization. I haven't checked if that factorization works, but I'll trust that it does. So yes, you could do that, I would say. And then you get 3 delta squared plus 7 delta. Now, though, the only issue with this Genjun, is like, how do you choose delta to guarantee that 3 delta squared plus 7 delta is less than epsilon? It can totally be done, right? There is a way of doing that, but it doesn't work out as cleanly as just saying, let it be epsilon over 7, right? Now you've got this sort of like quadratic in deltas that you need to be less than epsilon. And you're going to end up evoking some sort of weird, like it can be done. It's going to be a little bit messy, I think, if you do it that way. So it just makes life a little bit easier, right? Yeah, sorry. This thing in the box isn't related to the problem. Maybe let me use different numbers so we don't confuse it. Right? I was just kind of making this point that people get upset when you write less the equal to part here. And that you shouldn't be worried about that because, yeah, it's not equal, but who cares? And then, yeah, as said, like, you know, the 7 comes from the 3x plus 4. Okay. So again, this is the rough work. You actually have to do the proof, right? Like, this is not how you do the proof. You would say let epsilon be greater than 0. Choose delta to be the min of epsilon over 7 and 1. Then you can reference this rough work. That's how you'd actually do the proof. So I'm going to leave that to you. You can work that out on your own. Okay. And that's how you do it. And again, easy to practice. Choose whatever crazy piecewise function you want and start plugging things in and do your own proof, right? It's easy to create practice questions for this. And then hopefully you have a friend in the class. Hopefully you've all been trying to, you know, get to know each other. And so you can make a question. If you want to practice epsilon delta, make a question, give it to your friend, have your friend make a epsilon delta question, give it to you. Both of you work on those questions separately and you trade them back and you compare your answers and see if you both got basically the same thing or both have reasonable arguments and rationalizations. And if you do, then phenomenal, right? You know that you got it right. So it's very easy to make example problems for this. I would recommend that as a general rule, stay away from the exponential and logarithm. Technically, we haven't defined them yet. It's not impossible to work with them, but it's a little bit tricky. Trigonometric functions are a nightmare, so don't yet try and do anything with trig functions. Kind of stick to polynomials, rational functions, square roots, nth roots, things like this along these lines, piecewise functions, and make your examples out of those. Because the transcendental functions like the exponentials and the trigonometric functions are a little bit tricky, and we need a little bit more tools before we can really play with them, right? Again, they're not impossible. If you really want to challenge yourself, you know, go crazy. Okay, so that covers, you know, limits, the basics of like one-sided limits and two-sided limits. But what I want to do next is talk about like horizontal asymptotes. So, and again, if you're familiar with this, the idea is that if you look at the graph of a function, you know, not all functions do this. So here's my y, here's my x. But the hope is that maybe for some functions that are really well behaved, you get something like this that maybe happens, right? And so as you shoot off to infinity, okay, you might never actually hit the line L, but you get arbitrarily close to it. And that word arbitrarily close is something, of course, that we've seen with limits before. So the question is, like, how do we change or adapt the definition of a limit in order to make sense of this statement, right? So this is our goal. We want to define what this means. So how do we define this? All right. And kind of without going through all of the motions again, basically what we want to do now is we want to replace the as x gets arbitrarily close to c, right? So we want to replace the as x gets close to c part of the epsilon delta definition with as x gets really, really big, right? Of the definition with as x gets really big. or maybe arbitrarily big, right? If that's what you want. So that's our goal, right? And if we can figure out how to rewrite the epsilon delta definition to replace as x gets close to c with the as x gets very, very large, then we'll have figured out what this notion of a limit is. And again, we call this a horizontal asymptote. Now, I want to emphasize some people in high school learned completely wrong things about horizontal asymptotes. They learned, for example, that the function could never be equal to the horizontal asymptote. And of course, that's nonsense because, you know, I could redraw this as something like this, right? Where it kind of oscillates on either side of the asymptote. And that's fine. That's still a horizontal asymptote. Or maybe it eventually hits the asymptote and then becomes constantly equal to the asymptote. That's fine. Both of those functions have limits as x goes off to infinity. And in both of those cases, we would say that L has a horizontal asymptote. So if any teacher taught you that you will get arbitrarily close to but never touch a horizontal asymptote, that's BS and that's wrong. It can happen, but it is not required to happen, okay? Exactly. Yeah, some functions can go through it and some functions can just eventually become constant. Like the constant function, f of x equals 7, has a horizontal asymptote at 7. It's stupid, right? Because the function is just constant, but it for sure has one. So if anyone ever told you that, that's nonsense. And it says they didn't actually understand what they were talking about, okay? So I'm just going to clarify that before we go on. I just want everyone to make sure that you understand that. So this is what it means to have a horizontal asymptote. We could put it into a definition. A function f has a horizontal asymptote at L if either, and again, I didn't say what the limit is x. I haven't even defined what this means yet. So we don't know what it means, but we'll do it in a second. Right? So if either the limit as you go to positive infinity or the limit as you go to negative infinity, as long as one of those is equal to L, then you have a horizontal asymptote, which means at most a function could have two horizontal asymptotes. It could have one horizontal asymptote. It could have no horizontal asymptotes, right? But as long as the limit as you go to one of the infinities exists and is equal to your number, then that's what it means for you to have a horizontal asymptote. Okay, so here's the actual definition. And again, you're going to have to figure out, I guess, let me try and put into brackets how you would change it if you went to negative infinity. Definition. So suppose f mapping D to R is defined on A infinity. Okay, and if you want to change it to the limit as we go to negative infinity, we would change it to this. For some A in R. We say that the limit as x goes to infinity, f of x equals L. If for every epsilon greater than 0, there exists some m in R such that for all x in R, if x is greater than m, and then for the other definition, you would switch that with x less than m. Then we get this, okay? So the thing in the square brackets, in case this is your first time seeing a definition written like this, the thing in the square bracket says if you want to change the definition for the limit as x approaches negative infinity, replace out the thing in the square brackets with the thing right beside it, right? So instead of a infinity, you would use negative infinity to a. Instead of x greater than m, you would use x less than m, right? And then you get exactly the same definition. That way you don't have to write it out twice. That's just what this is. It's kind of like mathematical laziness, but this is a common thing, okay? This isn't just me. This is how we do it. So again, if we parse this, we say, well, it looks very similar to the epsilon delta definition, but notably, where are the differences? The difference is here, right? And so now this is exactly what I'm saying. We've switched out this idea that as we get arbitrarily close to, as x gets arbitrarily close to c, with as x gets arbitrarily big. Right? It says, no matter what real number m you give me, if I go further than that real number, then I'm within epsilon of my limit. Let me go back now to my drawing. Okay, I'll come back down here so you can see this, but let me go back down to the drawing and again, kind of give you the geometric picture of this. The idea is that there's some point, so I'm going to draw my epsilon band here. So we still have an epsilon band, but we don't have a delta band anymore. That doesn't make sense. L plus epsilon. And we're saying there's some point, maybe it's here. I mean, we could have, there's a better M that we could have used for this, but whatever. It's saying beyond this point, the function always lies in the epsilon band. Okay, so there's some point M after which the function is always in the epsilon band. Does that make sense? And then as you shrink epsilon, the M is probably going to have to get bigger as a general rule, right? You're going to have to go further to guarantee that you're still within the epsilon band. But that, as you know, you have a horizontal asymptote as long as you can always do that. No matter what epsilon you give me, I can go far enough down that the function always stays within the epsilon band. And hopefully, again, if you think about, well, like, how does this break if I don't have a horizontal asymptote? You know, if the function either just oscillates arbitrarily often, but kind of stays in magnitude, doesn't kind of shrink in magnitude, or the function goes off to infinity, then no matter what epsilon band you choose, or eventually you can choose an epsilon band which is small enough such that the function actually leaves it, right? So if you think about that, hopefully you can see why that would be the case. So does this make sense geometrically, like why this is, again, the correct definition of what it means for the limit to exist as we go off to infinity? And of course, right, with the picture, you would draw the epsilon band in the other direction if you wanted x to go to negative infinity. Okay, hopefully. And again, if you're still just like typing it in the chat, you can say something. And maybe I should just say this means, you know, for all epsilon greater than 0, there's some point M after which the function stays entirely in an epsilon band. Right? So for every epsilon, you can find some point M after which the function always stays inside of that epsilon band. And I think that this is valuable. You do want to practice being able to take mathematical statements and kind of turning them into, I don't want to say pithy, but like, you know, some sort of English equivalent statement that helps you really get your head around the idea of what's happening. You have to be a little bit careful about these things because if you don't word them carefully, you could actually, you know, put yourself into a situation where you misunderstood what was happening. But nonetheless, this is how you actually remember things, right? You're probably not going to remember this chain of symbols that has for all epsilons and deltas. You're going to remember this English fact beyond some point, you know, for every epsilon, beyond some point M, you stay inside of the epsilon band. And that's how mathematicians actually remember things, right? And then we just reconstruct the mathematics based off of that understanding, right? We're not like robots. Okay, so that's the idea there. Let's do an example. All right, so this one's not super pretty, and I just whipped it up really, really quick. So there might be a better way, but whatever. I'm not worried about it. Okay, so yeah, we want to show that this is true, right? And again, if you've done any, you know, from your high school calculus, you would know that this limit is 1. You look at the coefficients of the terms in front of the x squareds and you divide them, and that's what your answer will be. In this case, it's 1 divided by 1, so we get 1. All right, and we're going to go straight to rough work in order to solve this. So I'm just going to immediately go to f of x minus L. That will be x squared all over x squared plus 1 minus 1, like that. And yeah, I mean, there's probably some more clever sort of like bounding arguments one could make here. I'm not going to worry about that. I'm just going to give them a common denominator. Very nice. We get some sort of cancellation of the x squareds. And in fact, even though the numerator left over is -1, because I'm taking absolute values, I know what the absolute value of -1 is. I can just actually completely get rid of the absolute values because I know that this term here is always greater than 0, right? There's no value of x for which this number is less than 0. So I can actually just get rid of the absolute values and make this equal to 1 over x squared plus 1. Now, I want this to be less than epsilon, right? So we want 1 over x squared plus x less than epsilon. X squared plus 1. Why did I write that? Or x squared plus 1 to be what, greater than epsilon? 1 over epsilon. And so I'm just going to solve this for x squared. Actually, let's just go all the way and let's just solve for x, right? So x has to be greater than root 1 minus epsilon minus 1. All right, and this will work as long as epsilon is less than 1, right? If epsilon is bigger than 1, I'm in trouble. But that's kind of okay because obviously we're only interested in what happens as epsilon gets small, but nonetheless, we kind of have to treat this as a special case, right? So this works so long as epsilon is less than 1. Let me put the 0 in here just to remind us it also has to be positive. So again, in terms of the proof, I actually would do this one in cases. I think somebody last time, the first time we mentioned this bounding argument was like, we might need to do cases. So in this case, I would actually, in the proof, break it into cases. So in the proof, I would do cases, right? So if epsilon is greater than 1, then we can just take m to be equal to 0. And then otherwise, if epsilon is less than 1, then we take square root 1 minus epsilon minus 1, like that. Right? And the idea here is, well, what do I want to say? Yeah, I mean, the function's always less than or equal to 1 anyway, right? So that you might be saying like, well, what is this case saying? And if you plot x squared over x squared plus 1, this function's always less than or equal to 1, right? The denominator is always strictly bigger than the numerator because the denominator is the numerator, but you've added 1 to it. So x squared divided by x squared plus 1 is always less than or equal to 1. So if you choose an epsilon which is bigger than 1, the whole function is in the epsilon band, and you could choose literally any number you want for m, right? So that's why I chose m is equal to 0, right? Yeah, this is exactly, this is rough work. This isn't the proof. So the proofs I kind of leave for all of you, right? Because I've probably done like 3 proofs now. So after that, you guys can work out the proof. But does that make sense? Right? Like this function, if you graph it, I'm not going to be exactly perfect. This function looks something like this. And it's actually always beneath L is equal to 1, right? And so if your epsilon is bigger than 1, then your function is always in your epsilon band. So you can choose any m you want. I said m is equal to 0, but you can choose any m that you want. Why did we ignore the negative root? I mean, you could use it, I suppose, if you want. It's just like when you choose a delta, any smaller delta will work. In this case, once you have an m that works, any bigger m also works. So when you're trying to figure out which m you should choose, you should definitely choose the bigger one. What I would recommend is that you actually try doing the smaller m, and I don't think it'll actually work. Okay, so if you take the negative root, here's what can happen. Let me redraw this. I really wish I had multiple colors now. So this, again, this function looks something like this. Okay. And again, I might not have gotten it perfect, and its inflections or whatever the case might be, right? But this is what this function looks like. And what I'm saying is if I choose some sort of epsilon band, so 1 plus epsilon, 1 minus epsilon, I want to, and remember I'm taking the limit as I go to positive infinity. I'm saying, look, m is about here. And so if I am to the right of this point, then my function is always in the epsilon band. But what's wrong if I take negative it? The negative square root? The negative square root is here. And it's definitely, it doesn't work, right? Because in particular, I almost immediately leave the epsilon band. Sure, I eventually go back into it, but I almost immediately leave it. So if you take the negative square root, it actually will not work, right? And you can try this if you want. See that it actually will break. So you do have to use kind of like some mathematical understanding of what the function is going to look like. But the safe way around this is, again, if you're given two numbers that are your candidates and you're taking a limit as x goes to positive infinity, always choose the bigger of them, right? Because there's never any harm in going further. If I let this be my m instead, that's also fine. That also works, right? If I know that it's in the epsilon band, if x is bigger than 7, then everything is also in the epsilon band if x is bigger than 1,000. So take 1,000 if you want instead. So if ever given the choice between two numbers, always choose the bigger one, right? Well, I did approve, Yang, I did approve, where did I do it? I think it was the very first one. There you go. There's this was a proof right here. Right, so this was not rough work. This was a full-on proof. Right? But yeah, if we have time, I can go through it again. I don't want to do this one just because it has a bunch of cases and it's kind of boring. Let's see if I can get another one in. Do I have a x goes to negative infinity example? No, and I don't want to start vertical asymptotes. Okay, here, let me give you just this kind of exercise that I want you to think about. Okay, I'm going to give you a couple of minutes to try and do it. So how do we define this? But Yang as well, the video for Tuesday was up and I did a bunch of proofs in that one as well. So if for whatever reason my proofs today have been unsatisfying, give that one a check as well, and then try to write the proofs up for this. And then if you can't and you're having trouble, throw it on Piazza, and I'm more than happy to help. But yeah, they're videotaped from Tuesday as well, right? So that should help. Okay, everyone. So I want you to spend a couple of minutes and try and figure out what this definition should be. All right, so we've got a bunch of infinities here. So I want to say that as, and again, this isn't the only way a function could fail to exist, right? The limit could go to negative infinity. It could just be like sine and oscillate. But I want to say it doesn't exist in a very particular way, right? As I go off to infinity, it also shoots off to infinity, right? What should the correct definition of this be? Okay. So if anyone managed to get it, I'd love to see it in the chat. I'll give you, oh man, just Steven, I assume you were already doing it. There exists N, there exists M. Very close, very close. I think there's, yeah, so you definitely have the right idea, but there might be a quantifier issue. Because I claim that every function does your definition. Right, it should be for all n. And now n doesn't have to be greater than 0, but it can be if you want it to be. So yeah, let's kind of do this. So exactly, so here, I'm gonna write it like this. I'm gonna use for all n in R, but then I'm gonna come back and talk and show you all about n greater than 0. So for all n in R, there exists m in R such that for all x, x greater than m implies f of x greater than n, okay? Now, exactly, so this is more or less it, just with, you have to put the for all there. Now, in both of these cases, because you're going off to infinity, if you want to use this, that's no problem. These are the same definition. Right? Because basically one is saying n can be any real number. The other one is saying n has to be strictly positive. But because they're getting, the basic idea is that n and m are getting both arbitrarily large. So it doesn't matter where we say they have to be bigger than, because they're getting as big as we want them to be, right? So I could say for all n greater than 1,000, there exists an m greater than 1,000,000, such that this is true, and that would still be an okay and equivalent definition. So if you want, here's a nice little exercise that will actually be related to your next assignment, which is posted on Quirkus, by the way. It's obviously not your first priority. There's a test today, but the assignment is up. So exercise is to show that these are equivalent. I.e. that one function that satisfies, well, tonight, Paul, right? It starts at like 9 p.m. tonight and goes into 9 p.m. tomorrow. But if one function satisfies the first definition, that if and only if it satisfies the second definition, right? That's what it means for these two things to be equivalent. And then choose something and try and show it goes off to infinity. Easiest thing to do, right? A nice little warm up would be this. And then as you want to get more and more complicated, try trickier functions, try quadratics, try see if you can do it. Add some things in there. See if, maybe let's do x squared minus x. That's a fun one, right? And see if you can do these proofs. So I'm not going to cover these. And again, the reason I want you to get good at this is because there are going to be a bunch of, oh, look, we could take the limit as x goes to positive infinity, negative infinity, c from the left, c from the right. And then we could say the limit is positive infinity, negative infinity, L, these sorts of things. And so there are a total of like 15 different limit definitions, depending on what combination of these things you use. I'm only going to give you like 4 or 5 of them, but the idea is that after you've seen 4 or 5, you should be able to create all 15 of your own volition, right? So exactly, great practice, figuring out what this definition is. And so as kind of homework, which again, you're not going to worry about because there's a test, but in terms of homework, what should the definition of a vertical asymptote be, right? What should it mean to say the limit as x approaches 0 causes the function to go off to infinity, right? So see if you can write down that sort of thing as well. Okay, everyone, but otherwise I think that's it for us today. That finishes us up. Our vertical asymptotes, well, they're the same except that they're vertical, right? So a vertical asymptote is like this. So maybe this is C, and then they go, whoop. That was a terrible function. Right? It's like the Atari sign. Right? Vertical asymptotes can't cross because if they came back, they wouldn't be functions anymore, right? So the horizontal ones, you can cross as many times as you want. That's a function. It's not injective, but it'll be a function. With the vertical, if you cross, then there's no way you can ever come back, right? Because then you would fail the vertical line test. So in that case, you probably weren't lied to, but see if you can come up with the definition for this thing. Okay, everyone? So I think that's going to finish us off for today. Again, keep an eye out. You'll get an email around 9 p.m. telling you exactly where the test problems are. If you can't, or for whatever reason, if you don't get that email, like maybe Acorn is not configured correctly in Quarkus and it goes to, I don't know, some high school account or whatever, it's in the evaluations tab under the term test, right? Like right where it says term tests. So actually, I'll just share my screen to show you. Yes. You should just read procedure for term tests. Or actually the test paper itself will have it, what you can and cannot do. Basically, you can't use other humans. So you can't, ask your friends, don't ask Stack Exchange, don't look up answers. But if you want to use a calculator, it's fine. Calculator won't help you. If you want to use your notes, it's fine. That sort of thing, right? Everything says here, and the test will be right here. Okay, so where it currently says TBA under test 1, you will get the problems will be posted here, but I will also post them in the Quarkus when I post them. There are 3 questions, but I mean, who knows how many parts each question has, right? If each question has 10 parts, then it's like a 30 question test. And yes, Stephen, right? 9 p.m. Thursday to 9 p.m. on Friday. So you have 24 hours to do the test. And it's not time limited, right? You have the entire 24 hours. Yeah, exactly. I mean, it's the sort of thing that's common sense in an open book test, right? Is that you can't talk to each other, you can't seek outside help, but other than that, you can pretty much use whatever you have access to, right? That's the idea. I've written the test, so it should be writable in about an hour and a half. So you're going to want to find an hour and a half window somewhere. You might want to give yourself about 2 hours, though. I think 2 hours is a reasonable amount of time to kind of like look at the question, think about the questions. Because it's 24 hours, though, of course, you could look at the questions and then, take a nap and then come back and do them later. I suggest in any case, you should look at the questions as soon as you have them, as soon as they go up. Even if you don't plan on writing until, say, 12 hours later, look at the questions just so you have them in your brain and you can kind of like be thinking about them in your subconscious. Okay. What if you're stuck? Well, like, what if you were stuck on a test, right? There's kind of a SOL factor there that you kind of out of luck. But everyone, a note as well here, if you're in doubt about something, you should just ask, right? Ask me privately on Piazza, make it a private post though. Obviously don't ask that one in public. Send me an email, whatever the case might be. The worst that happens is I say, I can't help you because it's a test question. But to lose marks because you misunderstood an instruction that's a dumb way to lose marks, right? So worst case scenario, just ask and I'll tell you either the answer that you want, or I'll just say, yeah, I can't answer it, right? So always ask if you're not certain. We can exit the test whenever you want. Yes. Do your videos count as notes? Yeah, you can totally use the videos. Yeah, you can use any class resource for sure. Any resource that we have in class, the book, your notes, the videos, anything like that is a fair resource. You can try and use the TAs, but they'll probably tell you no. So yeah, that stuff is all okay. And again, if you're not certain, ask, right? If it comes up to a term test and you're like, hey, listen, I want to use like this YouTube video that I found, like, can I would say try and stay away from that, because that's kind of like using another human. But if you're not certain, you can ask, right? And I'll make a call at the time. It does not come in an electronic version, no. The bookstore is kind of weird about this because they're the ones who publish it, so they don't want to like electronic version out there, but the libraries actually have one. For those of you who are near enough campus, the libraries all have a reserve copy of those books. So you can go find them if you really want to, and then just photocopy them like crazy, take pictures. Okay, so like I said, they will be here. If you don't get the email at 9 o'clock, then the test questions will be right there. Okay, so that's how you figure that out. All right, everyone. Otherwise, we're good. No problem, everyone. Good seeing everyone. And, other than writing the test, I don't think I'm going to see you. Oh, and obviously, by the way, another reason, very, very quickly, another reason for you all to read the test questions carefully is you don't want to be trying to ask me questions at 7 p.m. on Friday, right? Because at 7 p.m. on Friday, I might not be around my computer. However, I will be, staring at my screen all day tomorrow from like reasonable times, like 9 a.m. to 5 p.m. So read the questions ahead of time. That way, if you have a question about a question, you can be assured that you'll probably get a response. If you're asking at 7, 8 p.m. on Friday, you're probably not going to get an answer, right? So make sure that you look at the questions ahead of time, so you have time to ask me questions about wording or interpretation. All right. But yes, thank you, everyone. Married student, 9 p.m. tomorrow. If we don't know a term, yeah, absolutely, you can ask Matthew. And again, like, what's the worst that could happen? I could say, like, you should know what that word means. Or if it's like, English is a second language thing, I can clarify it. That's not a problem. But always ask, because again, what's the worst that can happen? The worst that can happen is I say, I can't answer that question, right? Like if you ask me what is a limit, I'll say, well, that's in your notes. You can go look that up. But worst case scenario is I just say, yeah, I can't answer it, right? So always ask. No, it's going to be posted at 9 p.m. tonight. All right, thanks everyone. See you later. Mary, you can, if you read, go read the term test portion of the syllabus, and there are more instructions there. All right, thanks everyone. See you later. I'm gonna kill the meeting now. See ya. Have a good weekend.